We tend to imagine danger in the ocean near the surface. Sharks, teeth, movement in clear water, but most of the ocean is not blue. It is black. Beyond about 1,000 meters sunlight no longer reaches. There is no sunrise, no shadow, no color. The largest habitat on Earth begins there. Pressure increases with every descent. By the time you reach the deepest trenches, it is more than 1,000 times stronger than what your body feels right now. For a long time, scientists assumed very little could survive there. They were wrong. When cameras first began to return images from the deep, the animals did not look familiar. Some produced their own light, some were nearly invisible, some had jaws too large for their bodies, some appeared unrelated to anything near the surface. This is not just a darker version of our world, it is a different one. In parts of the deep ocean, life does not rely on sunlight at all. It survives using chemistry rising from the seafloor. Energy comes from rock and heat instead of the sky. Food is rare, encounters are rare, and evolution has had millions of years to experiment in isolation. Most of this world remains unexplored. So what does life become when it evolves without light? What changes when pressure is constant and food is uncertain? Why do some deep-sea animals look less like fish and more like something imagined? Tonight, we descend into the largest and least understood habitat on Earth to examine some of its unusual life forms. But before we begin, if you enjoy calm journeys like this, I'd truly appreciate a like or a subscribe. And if you'd be so kind, let me know in the comments, where are you winding down from tonight, and what time is it there? I always love seeing how far these late-night explorations travel. Now take a slow breath, and together, let's descend into the deepest ocean and see what evolution has built slowly and relentlessly over hundreds of millions of years beneath crushing darkness. Depth reveals itself not as distance, but as layers of change, each stratum of water carrying its own physics, its own quiet rules. Oceanographers divide this vast column into zones, not as borders drawn on maps, but as thresholds where light, warmth, and chemistry surrender piece by piece. The sunlit layer rests above thin as a veil where brightness still lingers. Beneath it lies the twilight region, where illumination fades into dim cobalt. Below that spreads the midnight zone, then the abyssal plains, and deeper still the trenches, each descent marked not by color, but by transformation. Light fades because seawater is a patient filter. Every meter absorbs a portion of the sun's spectrum, reds vanishing first, then oranges and yellows, until only blue remains, and even that dissolves into obscurity. Without photons, photosynthesis falls silent, and the architecture of life must rely on other currencies. Pressure gathers with steady persistence. Water is heavy, and its weight presses from all directions at once. Proteins, those delicate molecular machines folded into precise shapes, begin to warp under such force. Cell membranes, normally fluid and flexible, risk stiffening like chilled oil. Deep-dwelling organisms carry subtle chemical adjustments within their tissues, compounds that brace structures and keep reactions flowing, even when the surrounding sea would crush unprotected forms. Creatures from shallower realms seldom endure such descent. Gas-filled spaces within their bodies compress rapidly. Nerves misfire and enzymes lose their functional contours. Survival here requires blueprints written for compression from the beginning, not borrowed from brighter waters above. Temperature joins pressure as a quiet sculptor. Cold slows the jittering dance of molecules, and metabolism follows that slower rhythm. Hearts beat with unhurried patience. Growth stretches across years, and movement becomes deliberate, as though time itself thickens. Nourishment drifts sparingly. No forests of algae sway in these depths, no daily bloom of plankton. Instead, sustenance arrives as a gentle fall of fragments known as marine snow, a soft rain of discarded scales, microscopic shells, waste, and the remains of distant lives. Each particle is a parcel of stored sunlight from far above, sinking through kilometers until intercepted or settled. Sight adjusts to this dim dominion, where brightness never visits elaborate eyes, offer little advantage, and many inhabitants reduce them or abandon them entirely. Others enlarge their lenses into wide collectors, tuned to detect the faintest glimmer. Vision becomes less about detail and more about sensing presence, a negotiation between energy spent and information gained. In such surroundings, efficiency governs every design. Muscles favor endurance over speed. Bodies favor shapes that conserve rather than expend. Even behavior follows this arithmetic with long stillness, punctuated by brief action. Energy is treated not as a constant supply, but as a rare mineral, budgeted with exquisite care. Through these layered conditions, the deep ocean defines its character. It is not merely a place of depth, but a system of constraints that guide evolution along unusual paths, shaping forms and strategies suited to wait cold darkness and scarcity. Within this immense volume, life persists by aligning itself with the rules written in water and pressure, and once those rules are understood, the inhabitants that follow begin to seem less strange, as though they belong precisely to the world that formed them. Currents wander slowly across the sea floor, carrying traces of minerals and faint chemical signals that living sensors can taste. Nothing is wasted here. Every motion, every structure, every flicker of awareness reflects negotiation with an environment that gives little freely, yet offers quiet stability to those shaped carefully enough to remain. Balance is the final law here. A single filament of light drifts through the water, wavering like a thought that has forgotten its dreamer. It belongs to a hunter whose body seems almost an afterthought, a small dark form trailing beneath its own lantern. The glow does not spill outward. It gathers close a private star suspended from a slender spine that arches over the creature's head. This living lure is not decoration, but strategy. Tiny organs within it host colonies of luminous bacteria, and the fish feeds them with careful chemistry, so their glow continues without pause. In a realm where meals seldom pass within reach, such radiance becomes a promise. Small wanderers approach drawn by instinct toward any suggestion of sustenance, and the distance between curiosity and capture vanishes in a single motion. The mouth that receives them appears impossibly large, hinged wide enough to eclipse the rest of the body. Jaws unseal teeth, angle inward, and the surrounding water slips with the prey into a waiting throat. Ligaments stretch without protest. Bones flex instead of resisting. Nothing about the design is graceful, yet everything about it is precise, shaped by generations that survived only when opportunity was never wasted. Inside the stomach waits like folded cloth. It can unfurl to many times its resting size, accommodating meals that would seem unreasonable beside such a modest frame. Digestion proceeds slowly, extracting every fragment of nourishment, for another encounter may not arrive for days or weeks. The hunter drifts afterward, patient again, its faint lamp swaying gently as if nothing remarkable has occurred. Solitude defines much of its existence. Encounters with its own kind are so uncommon that reproduction follows a path unlike that of most animals. A male, minute and fragile compared with the female, lives chiefly to find her. When he does, he bites and holds. Tissues merge, skin joins skin, blood meets blood, until his body becomes an attached extension, sustained by her circulation. Over time, his organs diminish, leaving little more than the structures required to provide genetic material. He does not depart. He remains as long as she lives, a permanent companion, shaped by rarity itself. Such unions speak quietly of distances measured not in meters, but in chance. To drift through vast water and meet another of the same species is an event so unlikely that evolution has chosen certainty over courtship. Fusion replaces searching, permanence replaces pursuit. The female continues her slow passage, bearing her living satellite, her lantern, and her expandable net of jaws. Every feature reflects strict economy. Fins are small muscles, slight coloration subdued. Energy is reserved for the instant that matters, the strike that must succeed. Even her bones are reduced lighter and less costly to maintain, while her sensory pores remain attentive to the faintest tremor. Far below the roots of ships and storms, she moves through her immense domain, neither hurried nor idle. The light she carries glows on a quiet signal in the water, and within that gentle radiance rests the story of a creature assembled piece by scarcity, until nothing unnecessary remained and nothing essential was lost. In the stillness around her, time seems to loosen its grip, allowing moments to stretch like soft threads. The glow above her mouth sways with each subtle shift of current, a pendulum marking intervals no clock records. Nothing is hurried, nothing is squandered. Existence here is measured in chances accepted and chances gone, and she embodies that arithmetic completely, a small drifting hunter carrying her own horizon of light wherever she goes. Silence attends her always, in patient orbit. Glass seems an unlikely material for a skull, yet in the deep water there drifts a small fish whose head is shaped like a clear dome, as though a bubble refused to burst and instead learned to swim. Within that rounded canopy, delicate structures float in transparent fluid, protected yet visible, their faint green lenses turned toward whatever traces pass above. This creature is known as the barreleye, a name borrowed from the tubular form of its eyes. They resemble twin cylinders set inside its head, each one capped with a vivid retina that can gather the slightest glimmer. Muscles pivot them with slow precision. At times they aim straight upward, watching for silhouettes crossing the distant glow far overhead. When feeding, they rotate forward, aligning their gaze with the direction of motion, a quiet, mechanical grace unfolding beneath the clear shield. The dome itself is not bone, but a resilient membrane, curved and seamless, filled with fluid similar to the medium surrounding it. This design reduces distortion, allowing light to pass with minimal bending before it reaches the eyes. In a place where illumination is scarce and fleeting, even small losses would matter. Transparency becomes a form of conservation, an optical economy that preserves every possible photon. Along the body, darker pigments absorb stray brightness, preventing reflections that might betray its presence. The fish holds itself nearly motionless, fins trembling only enough to maintain position. From a distance, it might be mistaken for drifting debris, another fragment descending through the column. Yet inside the lucid dome, perception remains active, scanning slowly, patiently. Such anatomy was once known, mostly from specimens brought to the surface in nets, their fragile heads collapsed and clouded. For many years, the living posture of the eyes remained uncertain, their true orientation guessed from preserved shapes. Only when remote vehicles began to wander the depths, with gentle lights and quiet propellers, did observers witness the fish intact, suspended in its native stillness, eyes tilting as if considering angles of an unseen geometry. The upward gaze serves a careful purpose. Many drifting organisms cast faint outlines against the dim radiance filtering from far above, and the barreleye reads these shadows the way surface creatures read tracks in sand. Its vision is tuned not for color or detail, but for contrast, for the subtle difference between presence and absence. Each detection is a possibility measured against the cost of pursuit. Its mouth is small, suited for delicate prey, and its movements remain restrained, conserving strength. Even the transparency of its head reduces the need for heavy protective tissue, a lighter architecture that demands less nourishment to sustain. Form and behavior echo the same principal refinement shaped by limitation. Inside that crystal canopy, the eyes continue their gentle rotations, never hurried, never still for long. The fish drifts, a living observatory, enclosed within its own window, carrying clarity with it through the immense dark, its silent vigilance sustained by a design that turns fragility into advantage and vision into survival. Gentle currents slide across the dome without disturbing its clarity, as if the water recognizes a surface akin to itself. Within, the eyes tilt again, tracing faint motions that no other hunter would notice. Nerves relay signals with economical pulses, and the small heart answers with steady rhythm. Everything about the creature speaks in quiet measures, from the angle of its fins to the translucence of its shield. It remains poised in mid-water, a drifting instrument tuned to the slightest variation, balanced between currents and stillness, soft and belonging completely to the quiet world that shaped it gently. Long before instruments descended into these depths, this hunter already traced its quiet roots, carrying a form shaped in eras when shorelines followed unfamiliar paths. The goblin shark moves with steady composure through its shadowed domain, its pale body unhurried its outline, unlike that of other sharks that share distant ancestry. Its skin bears a muted tone, soft as worn shell, and from its head extends a remarkable snout, long and flattened, projecting forward like a narrow blade. Along that length lie delicate sensory pores, able to perceive faint electrical traces released by living muscles. These signals drift through the water as subtle patterns, and the shark reads them with calm precision, adjusting its course as each pulse strengthens or fades. Beneath this elongated rostrum rests the mechanism that defines its singular design. The jaws remain folded close while it glides, teeth angled inward, expression almost reserved. When prey passes within reach, tension stored in elastic ligaments releases. The mouth surges outward in an instant, the entire structure extending away from the skull. This projection occurs in milliseconds, carrying the teeth forward before the body itself advances, a swift mechanical motion guided by flexible cartilage channels that ensure accuracy. The teeth are slender and nearly translucent, shaped for holding rather than tearing. They close around small fishes or drifting animals, securing them while the jaws slide back into place. The action ends as quickly as it began, and the shark resumes its gentle passage, the sudden transformation leaving only stillness behind. Observers often remark upon the ancient character of its face. The impression arises from proportions seldom seen among modern relatives: the length of the snout, the narrow hinges of the jaw, the modest placement of the eyes. Fossils from strata older than 100 million years display similar forms, suggesting that this arrangement proved successful long ago and required little revision. Time has not urged it toward change. Encounters remain scarce because the species inhabits great depths along continental margins. Understanding comes from brief meetings, a specimen lifted carefully from darkness, or a fleeting image gathered by a descending vehicle. Each sighting contributes another quiet fragment, a measurement of fin angle, a note of posture, a confirmation of tone knowledge, settling gradually. In motion, it shows no urgency. Broad fins hold it level, and a liver rich with buoyant oils helps maintain position without constant effort. Energy is spent sparingly. Rather than chasing, it listens through its skin for electrical whispers that reveal concealed life. The projecting jaws complement this patience, allowing capture without pursuit distance, closing in a single precise extension. Those who have watched it describe a composed presence as though it carries the memory of older seas within its form. Muscles shift beneath its skin with subtle coordination, guiding each turn without waste. Every contour reflects selection shaped by depth and restraint. It continues unchanged through waters that remember its earliest ancestors still. On the quiet floor of the continental slope rests a shape, so still it seems part of the ground itself, a patient outline pressed into sand and silt. This is the goosefish, sometimes called monkfish, a hunter that does not roam but waits, trusting stillness as its chosen method. Its body spreads outward rather than upward, wide and flattened edges, softened by fringes of skin that mimic the textures around it. Sediment settles across its back without sliding off, dusting it in the same tones as the seabed. Seen from above, it dissolves into the landscape, its form readable only to eyes trained by hunger or accident. The mouth defines its presence. It opens toward the water above like a cavern roofed in bone, immense compared with the rest of the animal. When closed, it appears as a curved seam. When opened, it becomes a sudden chamber capable of engulfing creatures nearly its own size. The motion is swift yet economical, driven by a rapid expansion of the buccal cavity that draws water and prey inward together. Just before that instant, a small appendage performs its quiet work. Rising from the head is a modified dorsal spine, slender and flexible, tipped with a subtle lure. The structure sways with minute muscular guidance, imitating the movements of edible life. Passing animals notice only a harmless morsel hovering above the bottom. They approach, guided by instinct older than memory. Contact triggers the strike. The jaws lift, the cavity expands, and the surrounding water folds inward. There is no chase, no struggle played out across distance. The event is contained within a single, precise action, after which the seafloor returns to calm and the hunter settles once more into anonymity. This method reflects the arithmetic of a realm where opportunity is uncertain. Muscles built for bursts rather than endurance conserve fuel. Bones remain light. Even the skin assists by hosting pigments that match mineral grains beneath. Everything unnecessary has been reduced, leaving a design devoted to waiting. It lives along descending margins of continents where slopes lead gradually into greater depths. Here currents carry faint traces of organic matter and the occasional wandering fish. The goosefish positions itself where such pathways pass, aligning body and mouth with invisible routes. Time passes without urgency. Respiration continues slow and steady while the lure describes its gentle arc. Though related distantly to the lantern bearer encountered earlier in our descent, this species embodies a quieter interpretation of the same lineage. Its lure does not shine. Its presence does not advertise. It relies, instead, on resemblance becoming a piece of terrain that happens to breathe. Small eyes rest atop its head, angled to watch the water above, while the rest of the body remains concealed. They register motion more than detail, signaling when something crosses the narrow field that matters. Nerves relay the message. Muscles answer without hesitation. So, it remains a still figure shaped by sediment and patience, demonstrating how predation can arise, not from pursuit, but from disappearance. How survival may depend on blending so completely with one's surroundings, that distinction fades, leaving only a mouth, a lure, and the quiet certainty of timing. Within this posture lies a long inheritance written not in speed, but in restraint. Generations have refined the angle of its jaw, the patience of its nerves, the muted palate of its skin. Each trait persists because it asks little and returns enough. The seabed accepts its presence without notice, and in that acceptance, the hunter endures quiet as stone and just as still. It waits as ages turn softly past. Not all survival depends on breath. In a layer of ocean where oxygen thins to a trace, a small cephalopod drifts with unhurried grace, its existence unfolding in conditions that would quiet the lungs of most other creatures. This is the vampire squid, a being whose life is tuned to scarcity so extreme that even respiration becomes a delicate negotiation. The water it inhabits holds only faint remnants of dissolved oxygen, a region scientists call an oxygen minimum zone. Here metabolism must soften its pace or cease entirely. The vampire squid meets this demand through chemistry written into every cell. Its tissues consume energy at a rate far lower than that of shallow-dwelling relatives, and its blood contains pigments with an unusual affinity for oxygen, gathering each molecule as though collecting rare coins. Its body appears almost ceremonial in shape. A soft cloak of webbing stretches between its arms, forming a dark canopy that can fold or unfurl with gentle, muscular pulls. When extended, this membrane turns the animal into a drifting silhouette of curved lines, neither jellyfish nor octopus, but something suspended between forms. The texture is delicate yet resilient, composed of flexible proteins that remain supple despite the surrounding pressure. Movement is never hurried. Small fin-like structures near its mantle beat slowly, guiding it through the water with minimal effort. Rather than jetting forcefully, as many cephalopods do, it prefers a measured glide that conserves strength. Each motion seems considered, as though the animal weighs the cost of action before committing to it. If disturbed, it does not flee in frantic bursts. Instead, it releases a cloud unlike ink, a luminous mucus that blooms outward in soft blue points of light. The particles shimmer briefly, distracting attention, while the squid drifts away on quiet strokes. Producing this display requires energy, yet the investment is brief and precise, a calculated exchange that favors survival. Its lineage reaches far into the past, extending back hundreds of millions of years to ancestors that swam in ancient seas. Fossil impressions and genetic studies both suggest that its basic design has endured with only subtle alterations, a testament to how well suited it is for its chosen realm. While other branches of the cephalopod family pursued speed or strength, this one refined endurance and restraint. Feeding follows the same philosophy. Rather than hunting large prey, it gathers falling organic fragments and tiny organisms from the water, drawing them toward its mouth with filamentous appendages. This quiet collection demands little exertion, aligning perfectly with a life governed by limited resources. Even digestion proceeds, gradually extracting nourishment with careful efficiency. Around it stretches a habitat where many animals cannot persist for long, their tissues deprived of the oxygen required to sustain constant motion. The vampire squid remains at ease. Within this sparse medium, its physiology balanced to match the environment so completely that what challenges others supports it. So it continues, a gentle figure suspended in dim water cloak, folding and opening with patient rhythm, ancient blood moving slowly through its veins, a creature shaped not for abundance but for absence, thriving where breath itself is rare and silence is the most reliable companion. Within its tranquil circuit, every organ keeps the same deliberate tempo, hearts pulsing softly, nerves signaling without haste, tissues enduring conditions that would silence swifter bodies. Nothing in its design urges excess or waste. It survives by remaining measured, by letting the surrounding waters set the terms of existence. And in that agreement between creature and place, its quiet life persists with enduring steadiness through uncounted ages onward in stillness. Color behaves differently in the deep. Blue persists the longest, traveling farther than any other hue, while warmer tones fade quickly and disappear. Yet within this blue-dominated world swims a predator that carries its own hidden spectrum, a dragonfish capable of producing red light where red should not exist. Its body is slender and dark, almost absorptive, blending seamlessly with surrounding water. Along its sides rest rows of small luminous organs, most of them emitting the familiar blue common to deep-sea life. These serve ordinary purposes, subtle signals and lures, suited to a realm accustomed to that shade. But beneath each eye lies something rarer, a specialized photophore that can release a dim red glow. To most creatures nearby, that glow remains invisible. Their visual systems evolved to detect blue wavelengths, the only light naturally available at such depths. Red does not travel far from the surface, and so the ability to perceive it offered little advantage for millions of years. Eyes sensitive to red would have been unnecessary and energetically costly. The dragonfish, however, altered that equation. Within its own retinas are pigments tuned to longer wavelengths, granting it the capacity to see the very color it produces. When it activates this hidden beam, it illuminates prey without announcing its presence. Small fishes drifting in darkness remain unaware that they have been revealed, their bodies reflecting a light they cannot perceive. In this quiet exchange, sight becomes a private language spoken by one participant alone. The head of the dragonfish carries another striking feature. Its jaws are lined with elongated teeth, thin as needles and slightly curved inward. Even when the mouth is closed, these teeth protrude, forming a cage of pale spines against its dark skin. They are not built for crushing, but for securing, ensuring that once a target is seized, it cannot slip free. Muscles along the jaw hinge respond with controlled precision. The dragonfish does not rely on speed alone, but on positioning and timing, drawing close before committing to the strike. Its body remains flexible vertebrae, allowing subtle undulations that propel it forward without sudden disturbance. This ability to generate red light required more than altered eyes. Biochemical pathways within the photophores produce specialized luciferins capable of emitting at longer wavelengths, a rare adaptation among deep-dwelling organisms. The reaction remains efficient, conserving energy while creating a glow sufficient for its purpose. Nothing about the display is bright or extravagant. It is measured just enough to reveal shapes within a narrow field. In this way, the dragonfish occupies a visual niche almost entirely its own. It moves through blue darkness while carrying a concealed lantern that paints the world in tones unseen by others. The advantage is quiet but profound, allowing it to inspect potential prey without triggering evasive responses shaped by blue light detection. Encounters with this species are infrequent, glimpsed in submersible footage or recovered specimens whose delicate features hint at their living posture. Observers note the interplay between its dark body and pale teeth, between the subtle red beam and the surrounding void. Each element contributes to a strategy based on secrecy rather than force. So it glides onward, a narrow silhouette in vast water, red light flickering softly from beneath its eyes, perceiving forms that remain unaware of being seen, embodying a subtle inversion of the deep-sea rule where illumination usually betrays, and here instead conceals. Far from the seafloor and far from the surface, there is a region where direction feels almost meaningless, a vast suspension where nothing anchors and nothing hurries. In this open water drifts the gulper eel, a creature shaped less like a hunter and more like a possibility. Its body is long and slender, tapering into a thin whip of a tail, while its head seems borrowed from another design entirely. The jaws are enormous, disproportionately large, hinged wide like the frame of a net. When closed, they form a narrow profile, but when opened, they expand into a circular gape that dwarfs the rest of the animal. Ligaments stretch, bones pivot, and the mouth becomes a sudden chamber, capable of enclosing whatever chance delivers. This architecture is not built for pursuit. The gulper eel rarely chases. Instead, it suspends itself in midwater, scarcely moving, allowing faint currents to carry it through the dark. Muscles remain relaxed, conserving strength. It waits with the patience of drifting seeds, its vast jaws held ready as though time itself might place something inside. At the end of its trailing tail glows a small point of light. This luminous tip sways gently, a quiet signal in the surrounding blackness. Tiny organisms drawn by instinct toward any glimmer approach to investigate. The eel does not rush to meet them, it simply allows the distance to close. When a suitable shape nears its mouth, the jaws unfold in a swift expansion, and water rushes inward, carrying the visitor with it. Inside, the stomach provides another marvel of flexibility. Normally narrow and modest, it can stretch into a translucent pouch, many times its resting size. A meal larger than the eel itself can be contained within this elastic chamber, the tissues thinning but holding the contents, settling as digestion begins its slow work. Such capacity reflects a life where nourishment arrives without schedule, and refusal would mean loss. The rest of the body remains understated, almost delicate. Fins are small, musculature is light. Even the skeleton is reduced, composed of softer elements that require little energy to maintain. Every feature suggests a creature designed not for strength or speed, but for endurance through uncertainty. Those who have glimpsed it alive describe a gentle posture, the long form hanging vertically or at a slight angle, as though listening for motion through the water. Its skin is dark and smooth, absorbing what little light passes, leaving the glowing tail as its only visible point. The effect is subtle, a single star attached to a drifting thread. Generations of such drifting have refined this design. Individuals that could accept the largest meals, that could wait the longest, that could spend the least endured, while others faded. Over time, the species became an embodiment of chance itself, equipped to seize fortune whenever it happened to arrive. So, it lingers in the immense column, jaws folded, tail shining softly, body scarcely stirring. Nothing about it presses the world for abundance. It simply remains available to it. A quiet participant in a realm where opportunity is rare and preparation is everything. Its presence defined by readiness rather than pursuit, and by a mouth shaped perfectly for luck. In this suspended life, success is never scheduled, only received. The eel accepts this uncertainty without resistance, its form a patient net cast into open water. Currents shift, distances change, and still it waits, sustained by the design written into its bones and skin, a design that trusts chance the way roots trust rain, knowing that eventually something will arrive. Silently it endures in quiet balance. Along the ocean floor walks a creature that seems assembled from segments of stone, its body layered in plates that overlap like ancient shields. The giant isopod moves with deliberate steps across the sediment antennae, extended as though reading textures written into the ground. It belongs to a lineage related to the small pillbugs found in gardens on land, and that resemblance lingers in its form. The body is divided into armored sections, each one edged and firm, creating a protective shell that resists pressure and the probing mouths of predators. This armor is not rigid like rock, but jointed, allowing the animal to bend and turn while remaining enclosed within its own fortress. Some individuals reach lengths approaching half a meter, far larger than their terrestrial cousins. This enlargement follows a pattern observed in several deep-dwelling species, a tendency known as gigantism. In cold, stable waters, large size offers quiet advantages. Greater volume allows tissues to store nutrients longer, and a broad body loses heat slowly, supporting steady internal chemistry. The isopod's pace reflects this measured existence. Its many legs lift and set down in unhurried sequence, carrying it forward with patient certainty. Nothing in its movement suggests urgency. It travels as though time were abundant, pausing, often testing the sediment with sensitive appendages that taste for traces of nourishment. Food does not arrive frequently in these depths, and the isopod's body is prepared for long intervals of absence. Its metabolism can slow dramatically, heart rate easing cells, reducing their demands. Individuals have endured for years without feeding sustained by reserves stored within their tissues. When sustenance finally appears, the animal consumes it readily, folding its legs around the offering and chewing with steady persistence. Its eyes, set wide apart, are adapted for low illumination, yet they remain modest in size. Vision is only one sense among many. Antennae provide chemical awareness, detecting faint signals released by decaying matter or distant organisms. Through these cues, the isopod navigates its expansive habitat, guided more by scent than by sight. The shell that protects it also tells a story of ancestry. Fossil relatives from distant ages display similar shapes, suggesting that this design proved reliable across immense spans of time. While continents shifted and climates changed, this lineage continued with only subtle alterations. Its structure already suited to the conditions it would encounter. Predators rarely trouble an adult giant isopod. The thickness of its plates and the curvature of its back make it difficult to grasp, and when threatened, it can curl slightly, presenting a hardened exterior. Defense relies not on escape, but on endurance, trusting the integrity of its armor. Across the seafloor, it precedes a living relic carrying echoes of ancient seas within its segmented frame. Each step presses lightly into the substrate, leaving temporary impressions that fade as particles settle again. The animal neither hurries nor hesitates. It simply continues, sustained by a body designed for scarcity, size, and patience. Its presence, a quiet illustration of how life sometimes answers hardship, not with speed or aggression, but with durability. Time passes around it without notice. Currents shift grains of sediment along its path, and still it advances with the same calm rhythm. Within its layered shell, organs work with patient consistency, sustaining a creature whose survival depends not on haste, but on persistence alone. In this slow procession lies a quiet testament to endurance shaped by depth and age. It remains, as it has long been, steady, armored, and enduring, a keeper of ancient design, moving softly through time and silt together without ever changing form. Some creatures move as if the water itself were thinking for them. In the far descending reaches, where weight and silence settle together, a small octopus drifts with a rhythm so gentle it seems less like swimming and more like breathing. This is the dumbo octopus, named for the soft fins that rise from its mantle like rounded sails. Those fins do not beat quickly. They wave slowly, pressing against the water with careful strokes that lift and guide the animal without haste. Each motion carries it forward in a quiet glide, arms trailing beneath like ribbons. The movement requires little effort, and that economy suits a realm where energy must be spent as sparingly as possible. Its body lacks the firmness seen in coastal octopuses. Instead, it is composed of supple tissue, almost gelatinous shaped, to endure the immense pressure of great depth. There are no rigid structures to resist the surrounding force. Everything yields, slightly flexing in harmony with the weight of the water. This softness is not fragility, but adaptation, a design that allows the animal to exist where denser forms would falter. The dumbo octopus lives deeper than nearly all of its relatives, descending to zones seldom visited by others of its kind. Down there, the seafloor stretches wide and quiet, marked by scattered outcrops and the occasional rise of mineral formations. It passes above these features with calm assurance, adjusting its fins to maintain a steady hover. Its arms carry rows of delicate suckers, each one capable of grasping small drifting organisms or morsels lifted gently from the bottom. Feeding is unhurried. The arms gather, transfer, release, a sequence performed with patient coordination. A thin webbing connects the limbs, forming a soft umbrella shape when spread, then folding again as the animal resumes its measured travel. Reproduction follows the same deliberate pattern. Rather than releasing many eggs to chance, the female places them one by one upon firm surfaces along the seabed, attaching each capsule securely before moving on. The embryos develop slowly within their translucent cases, nourished until they emerge as fully formed miniature octopuses prepared for solitary life. Encounters between this species and human observers remain uncommon. Only in recent years have descending cameras recorded it alive in its native depths, revealing its posture and motion in ways preserved specimens never could. In those recordings, it appears serene, fins opening and closing like quiet wings, body poised without strain. Color shifts softly across its skin, subtle tones passing like faint weather. Specialized pigment cells respond to signals from its nervous system, allowing slight changes that may help it blend with the dim surroundings. Nothing abrupt occurs. The transitions are gradual, almost meditative, as though the animal were reflecting the slow tempo of its world. It continues through that vast stillness, neither hurried nor still, a small figure sustained by gentle motion and yielding form, its presence illustrating how life can persist, not by resisting pressure, but by accepting it, completely becoming as fluid as the depths that cradle it. In this quiet existence, there is no excess, only balance. Muscles contract and release with measured timing. The heart circulates calmly, and the fins keep their steady cadence. The animal asks little of its surroundings, and in return, the environment allows it passage. So it drifts on a soft voyager in the abyss, carried by patience and by the subtle grace of a body perfectly suited to the deep. Silently, it remains an emblem of quiet adaptation, enduring where pressure reigns, and gentleness proves stronger than force could ever be in those depths below. In the deep pelagic dark, there exists a fish whose life depends on a single decision, a quiet calculation made in the instant it encounters something edible. This is the black swallower, a slender predator whose modest frame conceals a remarkable capacity, the ability to consume prey larger than itself. Its body is narrow and unassuming, scaled in muted tones that merge with surrounding water. The jaws, however, tell a different story. They hinge wide, with surprising reach, supported by elongated bones and flexible joints that allow the mouth to open far beyond what its size would suggest. When extended, the gape becomes a living net capable of enclosing animals that appear impossibly large beside it. Teeth line those jaws in backward angles, small but firm, ensuring that once something passes inward, it cannot retreat. The the swallower does not tear its meal into pieces. It takes the entire body at once, drawing it slowly into its throat through steady muscular contractions. This process can last many minutes, the prey disappearing inch by inch until only the tail remains, then that too is gone. Inside waits a stomach unlike that of most fishes. Its walls are thin and elastic, able to stretch outward as the meal descends. Folds unfold, tissue expands. What began as a narrow organ becomes a swelling chamber that can occupy much of the animal's length. Blood vessels adjust, delivering oxygen to surfaces now drawn tight, maintaining function, even as the structure enlarges. Such expansion carries risk. If the prey proves too large or begins to decompose before digestion finishes, gases may accumulate within the stomach. The swelling can lift the fish upward, altering its buoyancy, sometimes fatally. In rare cases, the stomach wall may rupture under strain. Yet evolution has not removed this dangerous ability. Instead, it has preserved it, because in a world where food appears unpredictably, the chance to accept an oversized meal outweighs the danger of failure. The black swallower, therefore, lives by a principle of rare abundance. It drifts through long intervals with little nourishment, muscles conserving strength, organs working at a measured pace. Then opportunity arrives without warning, and the animal must decide instantly whether to seize it. There is no assurance that another will come soon. The decision favors boldness written into anatomy. Observers who have encountered specimens sometimes find them with enormous shapes distending their bodies, the outline of the swallowed fish visible through stretched skin. These sights reveal the full extent of its adaptation, a transformation that seems to defy proportion, yet follows precise biological design. Ligaments hold, membranes endure, enzymes begin their gradual work. This strategy reflects a balance between scarcity and possibility. The swallower is neither swift hunter nor tireless searcher. It is an opportunist shaped to exploit fortune whenever it drifts close enough to grasp. Every element of its form serves that purpose, from the extensible jaws to the yielding stomach walls. So it moves quietly through its vast domain, slight in appearance, yet equipped for extremes, carrying within its structure the capacity for sudden enormity, a reminder that survival in such remote waters often depends not on constant success, but on the willingness to risk everything when chance finally arrives. From cracks in the ocean crust, the planet exhales. Along certain ridges and volcanic seams, seawater slips down into the earth, sinks through heated rock, and returns transformed. When it emerges again, it does not rise gently. It surges upward in dark plumes, carrying minerals dissolved from stone, forming what observers call black smokers. These vents release water heated far beyond the boiling point known at the surface, yet the immense surrounding pressure keeps it liquid. The fluid billows out like ink dense with iron sulfides and other compounds that crystallize as they meet the colder sea. Chimneys grow from these deposits, narrow towers rising slowly, their surfaces rough and glistening, their shapes changing as new layers settle. No sunlight reaches these depths yet. Around the vents gather dense communities of living forms. The foundation of this abundance is not light, but chemistry. Microbes thrive within the vent plumes, using reactions between dissolved minerals and oxygen to produce energy. Instead of drawing power from the sky, they draw it from the earth itself, assembling organic matter through a process known as chemosynthesis. In this way, they become primary producers, sustaining food webs without any reliance on photosynthesis. Among the most striking inhabitants are tube worms, pale and elongated, anchored in clusters along the vent structures. Their bodies extend from protective tubes topped by soft crimson plumes that sway in the rising currents. These animals possess no mouths and no digestive tracts. Inside their tissues live symbiotic bacteria that perform the chemical work of nourishment. The worms supply the microbes with hydrogen, sulfide, and oxygen absorbed from the surrounding water, and the microbes return sustenance synthesized from those ingredients. Around them gather other creatures adapted to the vent environment, small crustaceans, specialized mollusks, and pale fishes that weave through the mineral towers. Each species occupies its place within a system fueled by reactions rather than rays. The water near the vents may shift rapidly in temperature and composition, yet the organisms persist, their enzymes structured to function within these fluctuating conditions. The chimneys themselves grow and collapse over time. Minerals accumulate passages, clog, and pressure redirects the flow until a new vent opens nearby. Life follows these changes with quiet resilience. When one outlet cools and falls silent, nearby plumes continue to nourish their surrounding colonies. Movement is gradual, guided by chemical gradients sensed through delicate tissues. To witness such a place is to see a different version of Earth's living fabric, one in which the usual source of energy plays no role. The glow that sustains these communities is invisible, carried in molecular bonds rather than beams. Yet the effect is unmistakable, a thriving assembly sustained by the planet's inner heat. In these hidden oases, existence unfolds according to ancient rules. Long before forests spread across continents, similar chemical exchanges may have supported early life in primordial seas. The vent fields preserve that possibility in ongoing form, a reminder that vitality does not always depend on brightness, but can arise wherever matter and energy meet in suitable balance, even in the deepest reaches, where stone and water share their quiet conversation. Mineral particles drift like slow snow around the chimneys, settling on shells and skin without harm. The inhabitants remain composed within this shifting haze, their lives synchronized with pulses of heat rising from below. Nothing here depends on dawn or dusk. Instead, rhythms follow the steady breathing of the earth itself, and within that patient cadence, the vent communities endure, nourished by warmth drawn from the world beneath them. White threads drift from its arms like fine silk caught in water, though they are not threads at all, but living filaments growing from the shell of a small crustacean. This is the yeti crab, a pale inhabitant of vent fields whose appearance suggests frost rather than heat, whose limbs carry gardens instead of armor. Its claws are lined with dense bristles, soft and pale, forming thick fringes that sway gently with each motion. Along these strands, live colonies of bacteria coating the hairs in a faint sheen. The crab tends these microbial fields with deliberate care, holding its claws within rising vent fluids where dissolved chemicals stream upward from the seafloor. The bacteria feed on these substances, converting them into organic matter, and in time, the crab harvests them with slow passes of its mouthparts. This relationship is neither accident nor decoration. It is a partnership refined through generations, each participant sustaining the other. The microbes gain steady exposure to the compounds they require, while the crab gains nourishment without searching across the surrounding terrain. Its claws become both farm and pantry, a living surface that produces food continuously as long as the chemical flow persists. The crab's body is lightly pigmented, almost ivory in tone, a reflection of its lightless habitat. Eyes are reduced, their function diminished in a place where sight offers little guidance. Instead, sensory hairs and chemical receptors help it interpret the subtle signals carried in the water, informing it where vent currents pass and where conditions remain favorable for its cultivated companions. Movement is careful and measured. The crab positions itself close to vent openings, extending its arms into the mineral-rich streams, then withdrawing them slightly before the heat grows too intense. This gentle rhythm keeps the bacteria supplied while protecting the host from temperatures that could harm its tissues. It resembles a quiet dance guided by gradients of warmth and chemistry rather than by light. For a long time, creatures like this remained unknown to human observers. Only with recent expeditions using deep submersible craft did the yeti crab come into view, its pale form revealed against the dark rock. Its discovery added another chapter to the growing record of organisms that thrive in places once assumed barren. Each new descent has brought glimpses of forms unlike any imagined before, suggesting that vast portions of the ocean still hold inhabitants unrecorded. Within its small frame, the crab carries a system both simple and intricate, a collaboration between animal and microbe that turns mineral seepage into sustenance. The hairs on its claws provide structure, the bacteria provide chemistry, and together they create a quiet cycle of growth and feeding. No hunting is required, no chase across open ground. Nourishment rises directly toward it, and the crab need only maintain the delicate balance. So it remains beside the vent arms lifted slightly, filaments waving its cultivated coat, alive with unseen industry. In that gentle posture lies evidence of how life adapts when given time, and isolation shaping alliances that transform harsh surroundings into habitable ground. The yeti crab endures not through strength or speed, but through partnership, its survival, written in cooperation between species, a soft testament to the inventive paths evolution can follow in the hidden reaches of the sea. Around it, the vent field continues its slow transformations, mineral surfaces forming and fading currents, shifting their courses by subtle degrees. The crab adjusts without urgency, repositioning its limbs, tending its living harvest. Its existence unfolds in patient continuity, a small keeper of microbial gardens sustained by the planet's inner chemistry, and a reminder that discovery often begins with a single pale shape appearing where none was expected before. At a depth where the ocean presses with a weight difficult to imagine, a small fish glides just above the trench floor, its form so delicate it seems shaped from mist rather than muscle. This is the Mariana snailfish, a quiet resident of the deepest known waters recorded at depths beyond 8,000 meters, where pressure bears down with immense force. Its body appears almost translucent, soft and gelatinous, lacking the firm contours common to shallower species. Flesh yields gently when currents touch it, and that softness is precisely what allows it to endure. Instead of resisting compression, its tissues match the density of the surrounding water, preventing crushing gradients from forming across its cells. In such depths, solidity can be a disadvantage, while pliancy becomes protection. The skeleton follows the same principle. Bones remain thin and flexible, more like cartilage than rigid support. They bend slightly rather than fracture, distributing pressure evenly through the body. Joints move with quiet ease, guiding slow fin strokes that carry the fish along the trench slope. Nothing in its structure suggests strain. Each motion flows as though weight itself had become irrelevant. Within its cells lies an even subtler adaptation. Special molecules accumulate in its tissues, compounds that stabilize proteins against distortion. Under extreme pressure, ordinary proteins can lose their shape, folding incorrectly and ceasing to function. The snailfish counters this threat with chemicals that act like microscopic braces, preserving the precise forms required for life's reactions. Enzymes continue their work, membranes retain their fluidity, and signals pass along nerves without interruption. Its skin lacks heavy scales. Instead, it wears a smooth covering that allows dissolved substances to pass, easily aiding balance with the surrounding environment. Fins extend like soft fans, adjusting its position with gentle pulses. The tail sweeps slowly from side to side, each movement deliberate and efficient, suited to a world where rapid motion would demand unnecessary energy. Food here is sparse, and the snailfish accepts what arrives. Tiny crustaceans drifting near the trench floor become its meals, gathered with quick yet modest snaps of its mouth. Digestion proceeds, gradually extracting nourishment with care. Nothing is wasted. Every particle contributes to sustaining a life shaped for endurance rather than speed. The trench itself forms a long valley carved into Earth's crust, its slopes descending into shadowed distances. Along these contours, the snailfish travels, sometimes alone, sometimes passing others of its kind, in silent crossings. Their presence demonstrates that even the most compressed environments can support complex organisms when adaptation reaches deeply enough. Scientists who have observed these fish describe their movements as untroubled, their posture relaxed, despite the immense forces surrounding them. Such calm reflects a harmony between biology and setting. The pressure that would overwhelm many creatures becomes simply another constant, like temperature or salinity, integrated into the fabric of daily existence. So the Mariana snailfish continues along its quiet path, gelatinous body drifting, flexible bones, bending cellular machinery, held steady by invisible chemistry. It lives where weight is greatest, yet it carries no sign of burden, embodying the principle that survival in extreme realms often depends not on strength, but on transformation, at the smallest scales, where molecules themselves learn to endure. At first glance, it appears to be a single, elongated organism drifting through open water, its length trailing far beyond the reach of ordinary sight. Yet what moves there is not one creature, but many joined together in seamless cooperation. This is a siphonophore, a colony so integrated that individuality dissolves into collective form. Each siphonophore begins as a single fertilized cell, but as it grows, it does not develop into a solitary body. Instead, it buds, repeatedly producing specialized units known as zooids. These units remain physically connected, sharing tissue and nutrients, yet each takes on a distinct role. Some are devoted to propulsion, pulsing rhythmically to draw the entire colony forward. Others extend long tentacles armed with stinging cells designed to capture passing prey. Still others handle digestion or reproduction, ensuring continuity across generations. The result is an organism composed of many individuals functioning as one. Coordination arises through shared nerve signals and chemical communication flowing along the colony's length. When prey brushes against a tentacle nearby, feeding zooids respond in sequence, contracting and transferring the captured organism toward digestive sections. The process unfolds with quiet precision, no single unit acting alone, yet no confusion in the exchange. Transparency defines much of their structure. Many siphonophores possess bodies nearly invisible in water, their tissues refracting little light, their outlines dissolving into surrounding currents. Only subtle iridescent hues or faint luminous pulses reveal their presence. In dim mid-water, they drift like living threads, delicate yet effective. Some species extend astonishing distances. Certain colonies have been recorded measuring over 40 meters long, longer than many whales, yet far more fragile in appearance. Their length is not rigid but flexible, bending and coiling as currents shift. Along that length hang repeating patterns of zooids arranged with remarkable symmetry, each cluster positioned precisely relative to the others. Feeding relies on encounter rather than pursuit. The colony may trail tentacles behind it like an immense net, waiting for small fish or crustaceans to make contact. Once ensnared by stinging cells, the prey is drawn inward through coordinated contractions, moving along the colony until digestion begins. Energy gathered in one region becomes available to all, distributed through shared canals. Locomotion is equally collaborative. Specialized swimming units near the front pulse in rhythmic succession, producing gentle thrust that carries the entire structure forward. The movement is smooth, almost serene, as though the colony glides by intention rather than effort. Each contraction is modest, conserving energy while maintaining steady progress. Despite their complexity, siphonophores remain vulnerable. Their gelatinous bodies can be torn by rough disturbance, and their survival depends on maintaining integrity across many interconnected parts. Yet this very interconnectedness grants resilience in another sense. Damage to one zooid does not end the colony. Others continue their functions, compensating for loss. To observe a siphonophore is to witness individuality arranged into harmony. It challenges simple categories of organism existing somewhere between singular and multiple, embodying cooperation at a fundamental level. In the quiet reaches where it drifts its elongated form, traces patient arcs through open water, transparent sections, catching faint glimmers, tentacles extended with understated confidence. Thus, it continues, a living chain of specialized beings, united by shared purpose, moving as though guided by a single will. Within its drifting length lies a testament to how evolution can weave many small lives into one continuous presence, forming a hunter that is both colony and creature, both many and one, sustained by coordination and the subtle strength of unity. Light from far above arrives only as a faint suggestion, yet even that distant glow can reveal a silhouette to watchful eyes. In this dim middle realm swims the hatchetfish, a small creature shaped like a polished blade, its sides flattened and gleaming with a metallic sheen. Its body reflects like a mirror. Scales along its flanks are arranged in layers that scatter incoming light rather than absorbing it, sending it outward in softened flashes. This reflective surface does not shine brightly. Instead, it diffuses illumination, so the fish blends with whatever faint radiance surrounds it. Seen from one angle, it appears to vanish, its outline dissolving into the dim background. Along its underside runs another subtle adaptation. Rows of tiny light-producing organs glow with a controlled blue radiance. These photophores match the intensity of the light filtering down from above, a phenomenon known as counter-illumination. To a predator looking upward, the fish's belly does not form a dark shape against the faint brightness. Instead, it mimics the same tone, erasing contrast and making the animal difficult to distinguish from the water beyond. This balance must be precise. Specialized cells adjust the brightness of the photophores in response to changing conditions, brightening or dimming as needed. The fish reads the ambient light through its eyes and nervous system, then alters its own glow accordingly. It becomes a living equation, constantly solving for invisibility. Predators may approach from any direction in this open water, and the hatchetfish prepares for threats both above and below. Its reflective sides conceal it laterally. Its glowing underside disguises it from beneath, and its narrow profile reduces the chance of detection from the front. Even its large upward-facing eyes contribute, gathering faint traces of motion so the fish can adjust its position before danger draws near. During daylight hours, it remains in deeper layers where the remaining light is faint and steady. When night spreads across the surface, it begins a slow ascent. This vertical migration carries it upward toward regions richer in plankton and small drifting organisms. The journey unfolds gradually, fins moving in small measured strokes, body angled slightly as it rises through the column. Feeding occurs in these upper levels under cover of darkness. There it captures tiny prey, filling its slender stomach before beginning its descent again with the coming dawn. This daily movement links distant layers of the ocean, transporting energy between them in quiet cycles repeated across generations. Its form is compact muscles, firm but economical, designed for brief bursts rather than sustained speed. The mouth opens just enough to seize small morsels, then closes again as the fish resumes its careful hovering. Nothing about its behavior invites attention. It survives through discretion, trusting its layered defenses of light and reflection. Observers who have studied these fishes note how easily they disappear from view, even when nearby. A slight shift in angle, and the body merges with its surroundings, leaving only empty water where a moment before there had been life. Such vanishing acts are not tricks, but consequences of precise structure of surfaces arranged to guide light rather than resist it. So the hatchetfish moves within its shifting field of dim illumination, a small bearer of mirrors and measured glow, navigating a world where visibility means vulnerability and where survival belongs to those who learn to match the brightness around them so completely that their presence becomes indistinguishable from the sea itself. In that quiet alignment between body and light, it continues its gentle ascent and descent, tracing a path that few observers ever witness, sustained by a design that turns illumination into shelter and reflection into refuge, a subtle traveler whose safety lies in resemblance rather than escape, whose existence unfolds like a faint glimmer, passing unnoticed through the vast and patient dark. There are forms in the ocean that seem to belong more to memory than to the present shapes that move as though time has never hurried them. Among these is the frilled shark, a long and slender predator whose outline recalls drawings from ancient stone rather than sketches from modern study. Its body stretches like a ribbon through the water, flexible from head to tail, moving with slow undulations instead of sharp thrusts. This motion resembles the glide of an eel, the spine bending in smooth waves that pass along its length. Fins remain modest and set far back, allowing the trunk itself to provide most of the propulsion. The result is a style of travel that appears unstrained, as though the animal simply follows the path of least resistance wherever it goes. Along its throat lie 6 pairs of gill slits, each edged with delicate folds that give the species its name. These openings ripple faintly as water passes across them, drawing oxygen inward with steady rhythm. Most modern sharks possess fewer slits, yet this arrangement persists here, a feature carried forward from distant ancestry and preserved with little alteration. The head tapers to a rounded snout, and within the mouth curve rows of slender teeth, each shaped like a small trident. They angle inward, forming a cage that holds any captured prey securely. When the jaws open, the teeth flare outward, slightly ready to guide food toward the throat. The mechanism works with quiet efficiency, relying on placement rather than force. Fossil evidence places the lineage of this shark deep in geological time, extending back tens of millions of years. Through ages, when continents shifted and climates transformed, relatives of this form continued to swim in ancient seas. Many other creatures vanished during those intervals, yet this design endured its structure, already suited to conditions that demanded patience and restraint. Encounters with living individuals remain uncommon. Most knowledge comes from rare captures or brief observations, moments when the animal rises from its usual depths into regions touched by nets or cameras. Those glimpses reveal a creature that appears almost unchanged from its distant predecessors, its features echoing patterns preserved in stone. Its skin carries a muted tone, and its muscles move with measured coordination, conserving energy while maintaining control. The long body allows it to coil slightly when approaching prey, then extend with a gentle surge. Nothing about the action is abrupt. The motion unfolds like a slow release of tension, precise and economical. Within its tissues, processes continue at a calm pace, suited to cool water and limited opportunity. Growth is gradual, and life may extend across many years. Each trait speaks of endurance of survival, shaped not by speed or competition, but by stability across immense spans of time. So, the frilled shark passes quietly through its shadowed domain. 6 gill slits, breathing body, bending in soft waves, a living remnant of earlier oceans. It carries within its form the memory of eras long concluded, not as a relic frozen in history, but as an unbroken thread that has crossed ages of change without surrendering its design. In its presence, the passage of time feels less like a current and more like a vast stillness through which it continues to move steady and composed its ancient lineage, written in every curve, enduring not by transformation, but by remaining precisely what it has always been. Before eyes adjust to the dark, there is already light waiting there, not falling from above, but forming quietly within living tissue. In the deep ocean, illumination is an internal craft assembled molecule by molecule inside specialized cells. The source of that glow lies in a simple exchange, a luciferin molecule meeting its partner enzyme, luciferase, in the presence of oxygen. When they bind, electrons shift to a higher state, and then settle again, releasing their excess energy as visible light. This reaction unfolds with remarkable restraint. Almost all the chemical energy becomes radiance, not heat. In a habitat where warmth dissipates quickly and food is limited, such efficiency matters. Producing light without wasting fuel allows animals to shine only when necessary, conserving their internal reserves. The glow emerges cool and controlled, flickering or steady, depending on the arrangement of the organs that house it. Across vast stretches of the deep, that light is most often blue. The reason is written into water itself. Longer wavelengths, such as red and orange, vanish quickly as they are absorbed. Blue travels farther, slipping through the liquid medium with less loss. Over time, organisms that emitted blue gained the advantage of reach, and those that detected blue became better attuned to their surroundings. Physics shaped biology, and biology followed faithfully. Yet the chemistry behind the glow is not identical in every lineage. Different species may use distinct forms of luciferin, assembled through separate metabolic pathways. Some cultivate luminous bacteria within dedicated chambers, allowing symbiotic microbes to perform the reaction. Others manufacture their own compounds entirely. Despite these differences, the outcome appears similar, a cool shimmer piercing the dark. This pattern reveals convergent evolution, separate branches of life, arriving independently at the same luminous solution. Light in the deep is rarely ornamental. It serves as language, disguise, and lure. Subtle pulses may announce readiness to reproduce, each flash timed with precision so that only the correct recipient understands. In other cases, a sudden burst startles a predator, momentarily confusing its vision while the glowing animal slips away. The chemistry does not change, but the intention does. Predators often shape their photophores into bait. A small moving point imitates drifting prey, inviting approach. The unsuspecting wanderer closes the distance, and the deception completes its purpose. Some species direct their glow downward, matching the faint light filtering from above erasing their shadow and blending into the background. Others illuminate false features, shifting attention away from vital organs. The organs themselves may contain reflectors, lenses, and shutters, structures that focus or diffuse the emitted light. Nerves regulate timing, allowing patterns to ripple across skin or flicker in measured intervals. Even the placement of photophores follows careful design, arranged along flanks beneath eyes or at the tip of a tail, each position suited to a specific task. Within this chemical artistry lies a deeper truth. In a world absent of sunlight, illumination becomes an extension of the body's internal processes. It is not borrowed brightness, but self-made radiance generated by reactions that convert stored energy into visible signal. The Luciferin reaction, simple at its core, unfolds in endless variations, shaping communication, deception, and survival. So the deep ocean glows in scattered constellations, each point a testament to chemistry refined by necessity. The light is quiet, efficient, and purposeful, revealing that even in profound darkness, life finds ways to create its own, gentle stars sustained by molecules that have learned to shine without flame. Nothing announces its presence, yet it shapes every form that lives below. Pressure does not glow or ripple or cast shadows. It simply exists, increasing with depth, settling against bodies with steady insistence, an unseen sculptor guiding life into particular designs. At great depths, the weight of water presses from all directions, at once influencing structures down to the molecular scale. Proteins, which must fold into precise shapes to function, become especially sensitive under such force. If compressed too strongly, their delicate coils can distort, preventing them from carrying out the chemical tasks that sustain life. Deep-dwelling organisms counter this by producing stabilizing compounds within their cells, small molecules that brace protein structures and help them retain their proper forms despite the surrounding weight. Membranes face a similar challenge. These thin layers enclose each cell composed of lipids arranged in fluid sheets. Under intense pressure, ordinary membranes would stiffen, losing flexibility and impairing their ability to regulate what enters or leaves. Species adapted to depth adjust the composition of their membranes, incorporating fats that remain fluid even when compressed. This subtle alteration preserves the gentle motion required for transport and signaling, allowing cells to function as though the pressure were unremarkable. Air-filled spaces cannot endure such conditions. Gas compresses easily, shrinking as pressure rises. Any pocket of air within a body would contract rapidly, collapsing structures that depend on it. For this reason, creatures of the deep avoid internal gas chambers. Buoyancy is achieved instead through oils, gels, or tissues closely matched in density to seawater, ensuring stability without vulnerability to compression. These adaptations extend beyond anatomy into chemistry itself. Enzymes that guide metabolic reactions must maintain their activity despite forces that would slow or halt similar reactions in surface organisms. Special variants of these enzymes operate efficiently under pressure, their molecular surfaces shaped to resist deformation. Even genetic material is supported by protective solutes that guard its structure, preserving the instructions each cell requires. For humans, such conditions remain far beyond natural tolerance. Our bodies contain air spaces in lungs, sinuses, and other cavities, and our proteins and membranes evolved for comparatively gentle pressures. Without protective technology, descent into extreme depths would subject tissues to forces they cannot counter. Gas volumes would shrink, biochemical reactions would falter, and vital systems would fail. Survival there requires equipment that shields the body, maintaining internal conditions similar to those near the surface. Among native inhabitants, however, pressure is not an adversary, but a constant companion. Their forms reveal its influence in every contour, from flexible skeletons to specialized blood chemistry. Nothing about them resists the weight surrounding them. Instead, they align with it, distributing force evenly so that no part bears more than another. Over generations, this invisible sculptor has refined its creations, favoring those whose molecules remain steady and whose tissues yield without breaking. The result is a community of organisms whose existence depends on balance with a force that never relents and never rests. In that silent equilibrium, life continues its slow rhythms, cells dividing enzymes, turning membranes, shifting gently, all sustained within the steady embrace of pressure. What would crush one form becomes the foundation of another, and in that transformation, the deep ocean reveals how even the most relentless forces can become architects of resilience, shaping beings that endure by fitting perfectly into the ways. Weight that surrounds them always. In a realm where light seldom lingers, vision becomes a question of cost and return. Some inhabitants invest heavily in sight, enlarging their eyes into vast collectors that dominate their heads. Others relinquish vision almost entirely, allowing eyes to shrink or disappear, redirecting precious energy towards senses better suited to perpetual dimness. For species that retain sight, the eye transforms into a sensitive instrument. Lenses widen to gather every trace of illumination. Retinas expand layered with photoreceptor cells tuned to faint wavelengths. In certain fishes, rod cells multiply in extraordinary numbers, each capable of responding to the arrival of a single photon. Such sensitivity allows detection of minimal glimmers, distant flashes, or the subtle outline of a moving form against a slightly brighter background. Neural circuits connected to these eyes refine the signals further. Tiny electrical impulses travel to visual centers that interpret contrast rather than detail, recognizing motion and pattern rather than color. The brain does not waste effort on complex imagery. It focuses on essentials, distinguishing presence from absence, direction from stillness. Yet this capacity comes at a price. Brain tissue consumes energy steadily even at rest. Maintaining large eyes and the neural structures that support them demands metabolic investment. In a habitat where food arrives unpredictably, such expense must justify itself. If sight provides clear advantage, the cost is worthwhile. If not, evolution favors reduction. Many deep-dwelling organisms, therefore, follow a different path. Their eyes diminish, becoming vestigial or disappearing entirely. Skin may grow opaque over former sockets, and neural pathways, once devoted to vision, reroute toward other senses. Touch, vibration detection, and chemical perception assume greater importance. In darkness, the movement of water carries information as reliably as light, and specialized sensory hairs or lateral line systems interpret those subtle flows. Some crustaceans and fishes rely on chemoreceptors that detect faint traces of dissolved compounds, reading chemical gradients like invisible trails. Others sense minute pressure changes, identifying the approach of a predator or prey through the displacement of surrounding water. These abilities require far less energetic upkeep than complex visual systems. The decision between enlarged eyes and lost eyes reflects balance rather than deficiency. In regions where even minimal light persists, retaining vision can mean earlier detection of opportunity or threat. In zones of complete blackness, sight offers no return, and relinquishing it conserves resources for growth, reproduction, or survival, during long intervals without nourishment. Certain species exhibit intermediate forms, possessing modest eyes paired with heightened non-visual senses. This combination allows flexibility across varying depths, accommodating slight shifts in illumination. Evolution shapes each lineage according to its specific niche, refining anatomy over generations until cost and benefit align precisely. Within this spectrum of adaptation lies a deeper principle. Sensory systems are not fixed inheritances, but responsive structures molded by environment. Where photons are rare, they may be treasured and amplified. Where they are absent, they may be ignored without consequence. Thus, in total darkness, vision becomes either a finely honed instrument or an abandoned relic. Both strategies reveal careful calibration, a measured response to conditions that reward efficiency above all. Whether through vast light, gathering eyes, or through heightened perception of touch and chemistry, life continues to interpret its surroundings, guided by senses that reflect the quiet arithmetic of survival. In a world where light is scarce and energy must be spent with care, time moves differently in the deep, not because clocks change, but because life itself adopts a slower rhythm. Growth unfolds in careful increments, measured not in seasons but in years, sometimes decades. Creatures here do not hurry toward maturity. They expand gradually, tissues forming with deliberate restraint, as though each cell weighs its investment before dividing. Food arrives infrequently, and this shapes every aspect of existence. Muscles develop with economy, organs function at reduced pace, and metabolism settles into a low, steady burn. Energy is treated as a rare currency, saved whenever possible, spent only when necessity demands. Even movement reflects this quiet accounting. A glide replaces a dash, a pause replaces pursuit, and stillness becomes as valuable as motion. Such restraint often leads to remarkable longevity. Many deep-dwelling animals live far longer than relatives in richer environments. Their slow metabolisms reduce wear on tissues, and their sheltered habitats expose them to fewer sudden threats. Years pass, gently marked by subtle changes rather than dramatic transformations. Age accumulates like fine layers of sediment, each one thin yet enduring. Reproduction follows the same patient pattern. Instead of producing vast numbers of offspring, many species generate only a few, investing resources carefully into each one. Eggs may develop slowly, nourished over extended periods before hatching. Young emerge already equipped for independence, their bodies prepared for the demanding conditions they will encounter. This strategy favors survival over abundance, ensuring that each new life carries a strong chance of persistence. The pace of growth also influences size. Some animals remain small throughout their lives, conserving energy by limiting the demands of their bodies. Others grow slowly, but steadily, reaching maturity only after long intervals. In both cases, development reflects balance between available nourishment and biological cost. Nothing proceeds faster than resources allow. Within this measured world, patience becomes a defining trait. Predators may wait long stretches between meals, conserving strength until opportunity drifts near. Grazers sift the surroundings, methodically gathering what little sustenance they find. Even microscopic organisms divide at rates slower than those near the surface, their cycles stretched by the same scarcity that governs larger forms. Cells themselves mirror this tempo. Chemical reactions proceed at reduced speed, enzymes working deliberately, nutrients absorbed and used with precision. Waste is minimized, and structures are maintained carefully rather than replaced frequently. This internal moderation preserves function over long spans, supporting lifespans that would seem improbable elsewhere. The environment encourages such strategies by offering stability in place of abundance. Conditions change little across time, allowing organisms to rely on consistency rather than rapid adaptation. With few disturbances to force quick responses, there is advantage in endurance. Survival belongs to those who can persist quietly, maintaining equilibrium through prolonged intervals of stillness. So life here unfolds like a long breath, drawn slowly and released without haste. Each action carries intention, each growth stage unfolds with patience, and each generation continues the same restrained rhythm. Scarcity does not halt existence. It reshapes it, guiding evolution toward forms that thrive through moderation. In this quiet economy, vitality is measured not by speed or number, but by duration. The creatures of these depths endure through careful balance, their lives extended by the very limits that surround them. What seems sparse becomes sufficient, what seems slow becomes enduring, and within that gentle arithmetic, the deep ocean sustains a community defined by patience and time. Far above the deepest plains, life flourishes in brighter waters, and from that distant activity, a quiet descent begins. It does not fall in sheets or storms, but in a continuous drift of particles, each fragment small and unassuming. This steady downward movement is known as marine snow, a rain composed not of ice but of organic remains. Dead plankton form much of this falling material. Microscopic plants and animals that once floated near the surface complete their brief lives, and their bodies begin a slow journey toward the depths. Tiny crustaceans graze upon them, digesting what they can, then releasing compact fecal pellets that sink more quickly than the fragile cells from which they came. Mucus sheds skins, fragments of algae, and minute carcasses gather together into soft aggregates that resemble flakes drifting through dark water. As these particles descend, they do not remain unchanged. Bacteria colonize their surfaces, breaking complex molecules into simpler forms. Small animals intercept some of the fragments, capturing nourishment before it sinks farther. Each interception slows the descent, and each transformation alters the chemistry of what continues downward. What finally reaches the abyss is only a fraction of what began near the surface. Yet even that fraction sustains communities far below. On the seafloor, organisms await this constant rain. Worms extend from burrows, crustaceans sift sediment, and fishes patrol, slowly searching for fresh deposits. The material that arrives is not abundant, but it is dependable. Day after day, year after year, particles settle onto the plains, providing a baseline supply of carbon and nutrients. Without this rain, much of the deep ocean would lack the energy required to support complex life. Marine snow functions as a vast recycling system. Carbon fixed by photosynthesis in sunlit waters becomes part of living tissue, then part of sinking debris, then part of the deep sea ecosystem. Some of it is consumed and respired back into dissolved forms, eventually returning to surface waters through slow currents. Some becomes buried in sediments, locked away for geological timescales. Through these pathways, the ocean regulates its own chemistry, moving elements between layers with quiet efficiency. The pace of this rain shapes the lives of those who depend on it. Growth rates align with its modest supply. Reproduction remains measured, reflecting the limited but steady arrival of nutrients. Even microbial communities on the seafloor adjust their metabolism to match the cadence of falling particles. Nothing is hurried and nothing is wasted. Occasionally, larger pieces descend the remains of a jellyfish or the body of a fish, delivering sudden bounty to the depths. These events are rare interruptions in the otherwise gentle snowfall. Scavengers gather quickly, consuming what they can before the excess disperses. Yet it is the constant drizzle of smaller fragments that defines the true rhythm of the abyss. Through this endless descent, the surface and the deep remain connected. The actions of microscopic plankton influence creatures living thousands of meters below. A bloom in bright water becomes sustenance in darkness, transformed through countless intermediate steps. Thus, marine snow continues, its patient fall invisible from shore, yet essential to the hidden world beneath. Each particle carries stored sunlight in chemical bonds, and as it settles, that distant energy is released once more into living systems. In this quiet exchange between layers, the ocean sustains itself, recycling matter through a cycle as steady as gravity and as enduring as the sea itself. Beyond the abyssal plains, where the seafloor seems already remote and final, the earth folds inward once more. There, in narrow arcs and elongated chasms, lie the deepest parts of the ocean regions, known as the hadal zone. These trenches descend beyond 6,000 meters, forming long valleys carved into the planet's crust, places where one tectonic plate bends and slides beneath another, in a process that shapes continents and ocean basins alike. The walls of these trenches slope steeply, guiding sediments downward until they settle along the deepest axis. Pressure here reaches extremes unmatched elsewhere in the sea, and yet life persists within these compressed corridors. The hadal zone is not an empty void, but a network of isolated ecosystems, each trench separated from others by vast distances and intervening ridges. This separation encourages unique communities to arise, species evolving along independent paths shaped by confinement and depth. Among the most common inhabitants are amphipods, small crustaceans with curved bodies and active limbs. Some species thrive at depths exceeding 10,000 meters, scavenging fragments that descend from above or feeding on material that collects along the trench floor. Their bodies remain flexible, exoskeletons adapted to withstand immense pressure without becoming brittle. Movement is purposeful, but measured antennae, probing the sediment for chemical cues that signal nourishment. The formation of these trenches traces back millions of years. Where tectonic plates converge, one plate is forced downward into the mantle beneath the other. The descending slab bends, creating a long, narrow depression that can extend for thousands of kilometers. Earthquakes ripple along these boundaries, and volcanic arcs may rise nearby, yet, within the trench itself, the environment remains cold and dark, shaped more by gravity and geology than by surface weather. Sediments accumulate slowly in these depths, layering the floor in fine particles carried from distant shores. Organic matter settles there, as well drawn into the trench by its sloping sides. In this way, the hadal zone acts as a collector, concentrating nutrients that might otherwise disperse across broader plains. Microbial communities flourish within these deposits, breaking down material and forming the base of local food webs. Despite their remoteness, these trenches are not untouched by human influence. Expeditions have discovered fragments of plastic, even in the deepest reaches, carried downward by currents and sinking debris. These traces serve as quiet reminders that the surface and the depths remain connected, that materials introduced into the ocean can travel far beyond their origin. The organisms that inhabit the hadal zone endure conditions of extraordinary compression, yet their physiology reflects the same principles observed elsewhere in the deep. Flexible tissues, specialized cellular chemistry, and energy-conserving behaviors allow them to function where weight is greatest. Each trench hosts variations on these themes, subtle differences shaped by isolation and time. So the hadal trenches extend, like hidden seams along the ocean floor, narrow and profound cradling communities that thrive in confinement and darkness. Their formation arises from the slow movement of tectonic plates, their ecosystems, from the steady descent of matter and the persistence of life. Within these deepest valleys, adaptation reaches its quiet extreme, and the planet reveals another dimension of its capacity to sustain living forms, even in the most compressed and secluded spaces beneath the sea. Size in the deep ocean follows a different logic than in shallower realms. Creatures that dwell far below often grow larger than their relatives in brighter waters, a pattern known as deep-sea gigantism. It appears not as a rule without exception, but as a recurring tendency visible across unrelated groups that share the same remote environment. One influence arises from temperature. Cold water slows metabolism, reducing the rate at which organisms consume energy. When bodily processes proceed gradually, growth can extend across longer spans of time. Instead of maturing quickly and remaining small, certain species continue developing year after year, their tissues accumulating mass with patient consistency. The chill does not force enlargement directly, yet it permits extended growth that can result in impressive proportions. Oxygen also plays a quiet role. In deep waters, dissolved oxygen can remain relatively abundant, especially where cold currents circulate slowly. Because oxygen fuels cellular respiration, its availability supports larger body structures, allowing tissues to function without strain. With sufficient oxygen, even sizable organisms can sustain themselves while maintaining low metabolic demands suited to their surroundings. Examples of this enlargement appear in many forms. Amphipods in trench habitats sometimes reach lengths far beyond those of their shallow relatives. Certain sea spiders extend their legs across surprising spans, their delicate limbs drifting through the water like articulated threads. Giant sponges anchor themselves to the sea floor, their porous bodies filtering nutrients from passing currents. Even single-celled foraminifera may construct shells large enough to be visible without magnification, their intricate chambers expanding gradually as they grow. Large size can offer subtle advantages. A bigger body stores more energy, providing reserves that sustain an organism during long intervals between meals. Greater volume also slows heat exchange, helping maintain stable internal conditions in cold surroundings. For predators, increased scale may allow consumption of a wider range of prey. For scavengers, it may enable travel across greater distances without exhaustion, their movements measured yet persistent. At the same time, enlargement does not demand speed or strength. In these depths, survival rarely depends on rapid pursuit. Instead, it favors endurance and efficiency. Muscles may remain soft, skeletons flexible, and movements unhurried, all traits that complement substantial size without imposing excessive energetic cost. Growth becomes a long investment, one that pays dividends through resilience rather than agility. Not every species follows this path. Many remain small, their compact forms equally suited to the conditions. Gigantism emerges only where balance allows it, where oxygen, temperature, and food supply align in ways that support gradual expansion. Evolution does not impose size, it permits it shaping bodies according to what the environment can sustain. Over generations, these influences accumulate, guiding lineages toward proportions that might seem unexpected elsewhere. The process unfolds without haste, guided by the same steady pressures that govern all life in the deep. Each increment of growth reflects a history of survival, a record written not in speed or spectacle, but in persistence. Thus, the deep ocean hosts giants that owe their scale not to abundance, but to patience, chemistry, and time. Their presence reveals how environment can reshape the possibilities of form, allowing size to become an advantage where resources are scarce and conditions remain constant. In that quiet vastness, magnitude itself becomes another expression of adaptation, rising slowly from the interplay between cold water available oxygen and the long rhythms that define existence far below the surface. Distance in the deep ocean is not measured only in miles, but in barriers that cannot be crossed. Ridges rise like walls, currents flow in steady directions, and vast stretches of seafloor separate one habitat from another. Within these divisions, populations become isolated, and isolation becomes a quiet architect of change. When groups of the same species settle in different trenches or basins, they no longer exchange genes. Generations pass each lineage, shaped only by its own surroundings. Small variations that might once have spread across a broad range now remain confined, accumulating gradually within a single population. Over time, these differences grow more pronounced until the descendants resemble their distant relatives only in faint outline. Speciation unfolds through this separation. Mutations arise, subtle alterations in DNA that may influence color structure, metabolism, or behavior. In large, connected populations, such changes often disperse and blend, but in isolated environments, they can become defining traits. If a mutation helps an organism survive local conditions, it is passed forward generation after generation, while less suited traits fade. Slowly, a distinct species emerges, shaped by the specific demands of its secluded world. Trenches provide striking examples of this process. Each trench functions like a hidden valley, bordered by slopes that restrict movement. Creatures adapted to its depth and chemistry rarely travel beyond its confines. As a result, amphipods in one trench may differ markedly from those in another, their bodies reflecting separate evolutionary histories. Though they share a common ancestry, their forms tell stories written in parallel rather than together. Genetic drift adds another layer to this transformation. In small populations, chance plays a powerful role. Traits may become common not because they offer advantage, but simply because the individuals carrying them happen to reproduce more often. Over many generations, these random shifts alter the genetic makeup of the group. The outcome is not directed yet. It contributes to the gradual divergence between isolated lineages. Some inhabitants of the deep trace their origins to ancient branches of life that have persisted with little alteration. Sheltered from rapid environmental change, these lineages retain characteristics that vanished elsewhere long ago. Their continued presence offers glimpses into earlier chapters of biological history, as though fragments of distant ages remain preserved in living form. Such organisms are not relics in a museum sense, but enduring participants in ecosystems that have remained stable across immense spans of time. Isolation does not imply stillness. Within each separated habitat, evolution continues its slow work, refining structures, adjusting chemistry, and shaping behavior. The absence of outside influence allows these adjustments to follow unique paths, guided solely by local conditions. Diversity arises not from competition across vast ranges, but from quiet divergence within confined spaces. The deep ocean, therefore, becomes a mosaic of evolutionary experiments, each region hosting its own variations on shared themes. Species that appear similar at first glance may reveal profound differences. Upon closer study, their distinctions, the result of long separation and independent adaptation. In this way, geographic distance beneath the sea fosters biological richness. Barriers that limit movement also encourage creativity, allowing life to explore multiple possibilities at once. Across trenches, basins, and ridges, lineages continue to branch their histories, unfolding in parallel silence, shaped by isolation and time into forms found nowhere else on Earth. Long before human eyes arrive, the deep ocean keeps its own counsel, holding forms and motions beyond ordinary reach. To approach this hidden expanse, explorers rely on instruments that can travel where bodies cannot, machines shaped to withstand pressure and silence, while sending their observations back through long tethers of cable and signal. Remotely operated vehicles drift downward with deliberate control, guided from ships far above. Their metal frames carry cameras, articulated arms, and clusters of sensors that translate the environment into streams of data. Lights mounted on their exteriors reveal passing shapes and textures, allowing observers to witness scenes unfolding in real time, though separated by thousands of meters. Each descent becomes a quiet voyage of discovery, the vehicle moving slowly so its presence disturbs as little as possible. Alongside these mechanical emissaries, submersibles carry human occupants into the depths. Their spherical cabins are engineered to resist immense compression, enclosing passengers within a small pocket of surface-like conditions. Through thick viewports, they watch unfamiliar landscapes glide past their perspective, framed by glass, yet immersed in a realm few have visited directly. The experience is rare and brief, yet it offers a sense of immediacy no remote system can fully replicate. Even when no creature appears before a lens, evidence of life can still be gathered. Water itself holds traces of those who inhabit it. Tiny fragments of genetic material drift freely shed as cells, scales, or waste. By collecting samples and analyzing this environmental DNA, researchers can detect species without seeing them. Each sequence acts as a signature, revealing presence through molecular clues carried in the current. Such methods have revealed that the deep ocean contains far more diversity than once imagined. New species are described each year, their forms sometimes unlike anything previously recorded. Some are discovered through video footage, others through specimens gently retrieved, and still others through genetic traces that hint at organisms yet to be observed directly. The catalog of known life expands steadily, though it remains only a fraction of what exists. Vast areas of the seafloor and midwater remain unexplored. The scale of the ocean alone ensures that many regions have never been visited even once. Equipment descends along chosen paths, yet between those paths stretch immense distances where no camera has looked. In those untraveled spaces, life continues unnoticed, following its own rhythms beyond the reach of observation. Technical limits also shape what can be found. Each expedition requires time, resources, and careful planning. Instruments must endure pressure, cold, and darkness, and their range is constrained by power and communication. Because of these limits, exploration advances gradually, charting small portions of a domain that covers most of the planet. Still, every journey downward adds another fragment to understanding. Images accumulate, samples are studied, and patterns begin to emerge. The deep sea reveals itself not all at once, but in glimpses, each one expanding the picture while leaving room for mystery. So discovery here proceeds like a slow unveiling. Machines descend, signals rise, and knowledge gathers piece by piece. Countless species remain unseen, not because they are rare, but because their world is vast, and our visits are few. Within that immense hidden expanse, life continues to flourish, quietly awaiting the moments when curiosity and technology together bring its presence into view. Long before forests spread across continents or animals walked on land, the planet was a very different place, its surface restless and its atmosphere thick with unfamiliar gases. Yet, In the deep ocean, traces of those distant ages still linger, preserved in environments that resemble conditions from Earth's earliest chapters. Hydrothermal vents rising from fractures in the crust release mineral-rich fluids heated by the planet's interior, creating settings that echo the chemistry and energy sources present billions of years ago. Around these vents, life thrives without reliance on sunlight. Microorganisms draw energy from chemical reactions between dissolved compounds, building organic molecules from simple ingredients. This process mirrors pathways that may have supported some of the first living systems long before photosynthesis filled the oceans with oxygen. The vent environment offers warmth, minerals, and chemical gradients, all elements thought to have played roles in life's earliest emergence. Observing these communities provides glimpses of how primitive metabolisms might have functioned when Earth was young. The deep ocean also preserves lineages whose ancestors extend far back in time. Some species display anatomical patterns that differ little from fossilized relatives found in ancient rock. Their continued existence suggests that certain habitats have remained stable enough to support consistent forms across immense spans of history. While surface environments experienced shifting climates, rising mountains, and changing seas, the depths often maintained steady conditions, allowing organisms to persist with minimal alteration. This stability becomes especially significant when considering mass extinctions. Throughout geological history, catastrophic events have reshaped life on Earth, eliminating large proportions of species. Asteroid impacts, volcanic eruptions, and rapid climate shifts have transformed ecosystems again and again. In shallower regions, such disturbances can be devastating, yet the deep ocean often buffers their effects. Temperature fluctuations remain moderate, and physical disruptions diminish with depth. As a result, some deep-dwelling communities endure when others vanish. Fossil records and genetic studies reveal that certain deep-sea lineages pass through extinction boundaries that erased many surface species. Their survival does not imply immunity, but it reflects the protective qualities of their environment. Reduced light, consistent temperature, and relative isolation combine to soften the impact of global crises. Over time, these survivors continue their quiet existence, carrying forward biological designs that originated in distant eras. Chemical signatures within deep sediments add further insight. Layers accumulate slowly, trapping particles that settle from above and preserving them like pages in a chronicle. By studying these deposits, scientists reconstruct ancient climates, ocean chemistry, and biological activity. Each layer holds information about conditions that prevailed when it formed, allowing the deep seafloor to serve as a natural archive of planetary history. Through such evidence, the deep ocean reveals itself as both refuge and record. Its environments resemble those of early Earth. Its inhabitants include descendants of ancient lineages, and its sediments retain memories of past worlds. Together, these qualities make it a living museum, not static, but continuous, where processes begun billions of years ago still unfold. In this quiet continuity lies a connection between present and origin. The same fundamental chemistry that once supported the first living systems persists in hidden places, sustained by heat from within the planet and minerals drawn from rock. By studying these depths, one observes not only unfamiliar creatures, but reflections of beginnings, reminders that the story of life is written across time as well as space, and that some of its earliest chapters remain active far below the chapped surface even now. Far beyond our planet, in the cold outskirts of the solar system, certain moons circle their parent worlds with quiet persistence. Beneath their frozen surfaces, Evidence suggests the presence of hidden oceans, vast bodies of liquid water sealed under layers of ice. Europa orbiting Jupiter and Enceladus, moving around Saturn, both reveal signs of subsurface seas inferred from gravitational measurements, surface fractures, and plumes of water vapor escaping into space. These distant oceans never see sunlight. Their surfaces remain locked in ice, reflecting faint rays from faraway suns. Yet tidal forces generated by their massive host planets flex their interiors, producing heat through friction. This internal warmth may keep water in liquid form, creating environments where chemistry unfolds in darkness, not unlike certain regions beneath Earth's own waves. On our planet, communities that thrive without light rely on chemosynthesis. Microorganisms harness energy from reactions involving hydrogen, sulfide, methane, or other reduced compounds released from the crust. Instead of drawing power from photons, they convert chemical gradients into biological fuel. This pathway demonstrates that life does not require direct sunlight, only a stable source of energy and access to liquid water. Because of this, Earth's deep ocean serves as an analog for those extraterrestrial seas. Hydrothermal vents and cold seeps illustrate how ecosystems might assemble in hidden waters elsewhere. If rocky cores beneath icy shells release minerals and heat, similar reactions could occur, generating energy-rich environments where simple organisms might arise. The details would differ, shaped by local chemistry and pressure, yet the underlying principle remains consistent. Life can emerge where energy flows through water and suitable molecules combine. Studying the depths of our own ocean refines the search for life beyond Earth. Instruments designed to detect chemical imbalances, organic compounds, or microbial signatures are informed by observations gathered here. When spacecraft analyze plumes from Enceladus or map the surface of Europa, they draw upon knowledge gained from vent fields and trench sediments. Each discovery in the deep sea expands the range of possibilities considered plausible on other worlds. The resilience observed in Earth's deepest habitats further broadens expectations. Organisms endure crushing pressure, scarce nutrients, and complete darkness conditions once thought incompatible with complex life. Their persistence suggests that extraterrestrial environments, once dismissed as inhospitable, may in fact harbor biological potential. Even simple microbial ecosystems would transform understanding of life's distribution in the cosmos. At the same time, caution guides interpretation. Earth provides only one example of life, and its pathways may not replicate elsewhere. Yet by exploring environments that approximate the extremes expected on icy moons, researchers test assumptions and refine models. The deep ocean becomes a natural laboratory for astrobiology, revealing how chemistry, physics, and biology intersect under constrained conditions. Thus, the study of remote trenches and vent systems carries implications that extend beyond our planet. Hidden oceans beneath ice, warmed by internal forces, may echo processes familiar from Earth's own interior. By observing how life persists in darkness, here scientists gain insight into what might unfold in distant seas. In this way, the deep ocean links planetary science and biology, reminding us that understanding the most secluded parts of our world also shapes the search for life in others, where water flows unseen beneath silent layers of ice. After all the miles of descent, after the instruments fall silent and the last images fade, the deep ocean remains, as it always was, vast, patient, and alive. It stretches across most of the planet, forming the largest living space that Earth has ever shaped, a realm so extensive that continents seem like scattered islands above it. Within that immensity, countless organisms continue their quiet existence, each one part of a living fabric that extends farther than any horizon visible from land. What appears unfamiliar there is not truly foreign. The creatures of those depths arise from the same shared ancestry as every living thing on the surface. Their forms may seem unusual, their movements measured, their structures, unlike those seen in shallower waters, yet each trait is simply a response to conditions that differ from those above. Pressure, darkness, and limited nourishment act not as obstacles alone, but as forces that guide design, shaping bodies into arrangements suited to their surroundings. Seen in this way, every unusual shape becomes understandable. Flexible tissues endure where rigid ones would fail. Subtle senses replace vision where light does not reach. Slow metabolisms preserve energy where meals arrive rarely. Each feature reflects a solution refined over immense spans of time, a quiet demonstration of how life adjusts itself to circumstance. Nothing there is arbitrary. Every detail carries purpose written into anatomy by generations of adaptation. The diversity of these solutions reveals how broadly life can interpret possibility. Evolution does not follow a single path. It explores, tests, and refines, producing forms that might seem improbable until the environment that shaped them is understood. In darkness and pressure, imagination expands not because nature invents at random, but because it responds faithfully to the rules imposed by physics and chemistry. Much of this world remains unseen. The distances are too great, the depths too demanding for exploration to reach everywhere at once. Between the places already visited lie vast regions where no lens has yet opened and no sample has been taken. In those unobserved expanses, ecosystems continue their steady rhythms, unnoticed yet undiminished, carrying on as they have for ages. Even so, each glimpse has altered perception. Discoveries from the deep have shown that life persists under conditions once thought impossible, that resilience can flourish in silence and obscurity. With every observation, understanding widens, revealing that the boundaries of habitability extend far beyond earlier expectations. The deep ocean becomes a reminder that the familiar surface is only one expression of Earth's vitality. As the journey concludes and attention returns to brighter realms, the depths do not recede or close. They remain below, layered in darkness, filled with motion too gradual for hurried eyes. Currents continue their slow passage, organisms follow their measured cycles, and chemical exchanges proceed without pause. The absence of witnesses changes nothing, so the descent never truly ends. It continues in thought, in curiosity, and in the steady unfolding of life, far beneath the reach of daylight. Long after lights are extinguished and vessels rise, that immense hidden domain persists, holding its communities in quiet balance. Within it, existence carries on, as it always has, shaped by forces older than memory and guided by rhythms that belong to the earth itself, enduring unhurried and profoundly alive.